Good evening, everyone. Okay. For the past 2 weeks, we've been working only on, I've been airing the videos on springs due to public interest. And one of the viewers, in fact, suggested that we also need to work on different topics. One of the topic was work energy theorem. And his query was, what is so special about work energy theorem and why should we work on it? If it is possible to showcase the differences between work energy theorem and the conservation of energy, because it has been derived from there. So it will be easy for us to get a breakthrough or get to know more about it, work energy theorem, because in the college, also in the school, also teachers usually say that work energy theorem is one of the easiest methods to solve problems. So why can't we do it? Okay, why should it be only work energy theorem? Why can't we use conservation of energy? So then I thought for a while and thought, okay, so instead of dealing with misconceptions, now for every problem related to work and energy, okay, why don't I find out a method, or why don't I describe both the methods, conservation of energy and as well as work energy theorem for a given question, okay, and solve it by both the methods. That's what I'm doing here. Okay, so one problem, two solutions. That's what we're going to do now. Okay, so now towards it, let us begin. So what is the speed of the particle of mass m due to free fall when it reaches the ground? Okay, so you have a particle of mass m. This is the ground. This is the height h. Now you are dropping it here. It reaches here. So what is he asking? What is the speed of the particle due to free fall when it reaches the ground? When it reaches this point, okay, before touching the ground, that's what I see. I put a small gap out there. What is the speed of the particle? Very simple. Conservation of energy principle. What do we do? Conservation of energy principle. We'll start with something like, what is the initial energy at this point? Energy at this point is nothing but mgh. Choosing this as my origin. And this is my x-axis and this is my y-axis. So if h is the height, so here the potential energy initially when the particle was about to be dropped is mgh, plus initial kinetic energy was 0 because we were just dropping it, right? This should now be equal to final potential energy. When it is about to touch the ground, the final potential energy is 0 plus final kinetic energy. See, when you are dropping it, because of gravity, it keeps on moving with a higher and higher speed. So when it comes here, definitely it has a velocity. Let us say here it has a velocity v. So this I can now write half mv square. So this now I can remove this m here, and thus I can write v square is equal to 2gh, or v is equal to square root of 2gh. This formula appears to be very familiar for you, right? Where did you learn this? In equations of motion. Now you can always ask me the question, so can I derive the same equation using equation of motion? Let us try doing that also. Okay, first method I have done. It's not mi, it is m1. Okay, now let us do with the second method. What's the second method? I didn't think that we can do it by equations of motion. So while I'm giving this lecture, I'm just thinking of why don't we do it by this method also. Now second method tells you, you can use equations of motion. Use equations of motion. So when can I use equations of motion? I can use equations of motion when acceleration is equal to a constant. When acceleration of a particle is equal to a constant. The moment you leave your fingers, the only force that acts on it is nothing but mg. Mg, the gravity, the weight acts on it. So therefore, if I write F equal to mg here, then the acceleration is nothing but F by m, which is equal to g, which is nothing but your 9.8, which is a constant. So I can definitely use equations of motion, nothing wrong. Now, how do I use? What is this velocity? Final velocity. So final velocity v square is equal to u square. What is u square? Initial velocity. U square, which is 0, plus 2 into g into, what is the height here? H, right? 2gh. So therefore, I can now write v is equal to square root of 2gh. The second method I have arrived at it. Okay. Now let us use some other method. I've already done using equations of motion. So why did I use it? Because of the fact that acceleration equal to a constant. You cannot apply this method everywhere. Okay. When the acceleration is varying, you should not apply this. Remember this. Then now let us look at the third method. What is this third method? Third method is your work energy theorem. Now, what is work energy theorem? Work energy theorem says work done is equal to difference in kinetic energy of the particle. Simple way to describe it. Now what we do know is, let us find out what is the work done in making this particle to start from here and to come here. What is the work done? mg is acting downwards. Work done is always given by f dot s. F dot s, right? So let us write f is a vector, s is a vector over here. So which should now be equal to, what is f here? F is nothing but mg, which is acting like this. What did we consider? Anything that goes upwards is positive. Anything that comes downwards is negative. Anything you are measuring downward is negative over here. So f is nothing but my mg. I'll just write this as mg. And then what is s over here? Yes, what is displacement? Displacement is also in this direction. Okay, displacement is also in this direction. Now, what is the angle between mg and s? Mg and s are f into f and s. It is nothing but 0 degrees. So I know mg dot h will now be equal to mgh cos theta. Now this should now be equal to mgh cos 0, which should now be equal to mgh. Okay, so the work done by the particle is equal to mgh to start from here and to reach here. Then what does it once again say? It tells this is equal to difference in kinetic energy. Okay, so difference in kinetic energy. What is difference in kinetic energy? What is the final kinetic energy here? Half mv square. Half mv square. What is the initial kinetic energy here? Half mu square. Half m into 0 square. So this should be equal to half mv square. Now I can equate these two, right? When I equate it, I get the answer as mgh is equal to half mv square. This m and m goes away. So thus once again I am left out with v square is equal to 2gh. Okay. Or I can write v is equal to root of 2gh, which is the same thing that we arrived here. Okay. So which method do you think is useful here? Or which method is easier for you? You can use either of these methods, nothing wrong. If you know whether the acceleration is constant or not, then definitely I'll say this method will be the most easiest one. 3 equations of motion, perfectly you can find out the rest of the parameters. Okay. But second method is conservation of energy is also good. This method is also good. Okay. Depends upon what is your exposure, how you have been using it. I've just taken a very simple problem to solve or to show this, okay, by all the 3 methods. In future, in the rest of the videos that you will be observing, okay, most of the time you will be either working out with work energy and conservation of energy, and to find out, okay, which method is useful. Thank you, friends, for watching this lecture. So if you like my videos, do subscribe to my videos, share it with your friends and relatives, so that it could also be helpful for them. And it really means something great for me if I have more number of subscribers. Thank you. Thank you very much.